The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Welcome everybody on this snowy Friday. At the end of last hour, and I just want to take a minute or two here to finish this piece up, we were talking about ways of writing kinetics expressions for a particular type of assumed ligand substitution mechanism. In particular, we were looking at dissociative substitution. And now, I'd just like to take you through what happens if you don't make the major assumption that we made last time, which was that every time our intermediate 5-coordinate complex ML5 was formed, it would go on to products. That was our assumption last time, one of them. And this steady state approximation is one that allows us to simplify the rate expression. If we don't make that assumption, what we say is that the change with time of the concentration of the intermediate is approximately 0. We know that at the very beginning of the reaction we have this ML5X species. X is the ligand that dissociates to give ML5. So at time 0 there is 0 ML5 concentration. And let me just remind you of this plot of what happens in a reaction like this. We have our initial ML5X species that decays away, and we have our product ML5Y that grows in. And if this reaction goes by dissociative ligand substitution, which would certainly be consistent with a D4 high spin electron count, as we saw last time, then there may be some intermediate ML5 that at time 0 has 0 concentration, and it may never really build up very much concentration, and then at the end it goes down to 0 too, because when the reaction's over, all of our ML5 has a Y attached and is 6-coordinate again. So if the concentration of the ML5 intermediate never really builds up very much, which is quite often the case, it may not even be observable, the amount of it which is produced during the reaction, then this approximation is pretty valid and allows us to derive equations for the change with time of the species that we can observe, namely the starting material that's going away and the product that's coming in. And so this is just our concentration versus time plot for the reaction. And with this approximation, we can then set equal to 0 the expression for the formation of the intermediate, which is K1 times ML5X. Okay? So this quantity, K1, if you remember back to the diagram we were using last time, K1 is the rate constant associated with surmounting that first energy barrier. K1 times ML5X, that produces ML5. So this is producing it, but when you're in the middle of the well where the intermediate lies, there are two ways to destroy ML5. You can go minus K minus 1 ML5 times X. This brings you then back over to where you started. And you can also lose it in a productive sense by K2 times ML5 times our species Y, which brings us on to products. And we're still making the assumption that once you get to products, the reaction is done and you never go back. Okay, so that assumption is built into this analysis. And if we look at this, we've set it equal to 0, meaning that ML5 isn't building up. And so now what we can do is we can rearrange this expression and solve it for the concentration of ML5. And you'll see that you can do that here. ML5 becomes equal to K1 times ML5X so you can see that. Divided, that's the expression for the formation. These two brackets should be gone. ML5x over k minus 1 times y plus, sorry, that's x, and that should be x here, plus k2 times y. So the expression in the denominator here are those two quantities that take us out of the well, and on the top we have the one quantity that takes us into the well from the starting materials. And so now we have an expression for ML5 that we can plug into our expression for the rate. So the rate overall expressed as the appearance of the final product is going to be equal to K2 times ML5. This is going over the final barrier times y. And so if we take the expression here for the rate, this is the value of that we expect for the appearance of products. We take that and we substitute in this expression for the unobserved intermediate ML5 into this. Then we have an expression for the rate entirely in terms of things that we can either observe, namely the starting material, the concentration we would measure by some technique like spectrophotometry as a function of time, watching an absorbance band for it decay away, for example. And then also in terms of the concentration of Y, which we were talking about as the solvent, so it would have a large invariant and known concentration. And then, of course, since X is being produced in the reaction whenever it dissociates from the starting material, there's a relationship between the concentration of X at any time and the concentration of our starting material at any time. So now we get an expression that we need to be able to integrate in order to actually produce, given these parameters, K1, K minus 1, and K2, to produce a predicted data set to compare with the experimental. And what one normally does is you take an experimental data set, you have the equations that arise from your mechanistic hypothesis, and you do a least squares fitting procedure to obtain the values of the parameters, which are these phenomenological rate constants associated with each step in the mechanism, extract the values of the parameters and see what you get, see if the mechanism that you've assumed can give you a good fit to the data or whether it can't. Okay, so that's the end of my discussion of an introduction to kinetic analysis of chemical reactions, a really important subject where differential equations really become very important. Now, today I want to get on to the topic of extended solids, and so I'm going to talk about dimensionality here. In materials. And I want you to keep in mind the framework with which we have been discussing chemical bonding all throughout this semester, because we're going to extend that today to try to understand some of the properties of systems that aren't molecular but extend infinitely in some number of dimensions. So we talked about the H2 molecule. This is a very small molecular system that we've described and talked about quite a bit. This system has a radius here of about 0.64 angstroms, or an internuclear distance of about 0.64 angstroms. And then we can also consider molecules that become more extended. There's an example of a polyene. Okay, and my use of a polyene here should lead you to think that when we consider polymer chemistry, in some cases we will be talking about systems that are extended, maybe not infinitely, but very greatly in one direction, or maybe more than one direction. But polyenes are interesting species because if this thing had all the double bonds trans as I've drawn here, then what we have perpendicular to the board would be a set of p orbitals, one p orbital perpendicular to the board on each of these carbons. And all of those p orbitals can overlap, and then we can start talking about the transport of electrons down a chain like this in one dimension. So I put H2 up here as an example of what is approximately a zero-dimensional system. Here's a system that extends somewhat in one dimension. And then as an example of a two-dimensional system, let me just draw up here a piece of one of the sheets of the graphite structure. So graphite is one of the allotropes of carbon, and graphite is a really nice 2D structure. I can draw in some of the unsaturation here. Okay, and I don't mean to suggest that this thing stops here. These carbons on the perimeter of the graphite system have bonds, and the structure looks very much like what I've drawn here if you repeat outward, up, down, left, or right. And what that leads to are two-dimensional planar arrays of carbon atoms that, as with the polyene structure, here this polyene that I drew with 6 bonds is about 13 angstroms long. And then the problem that you get to with graphite is that these graphite sheets can have dimensions of millimeters. So you get you've gone from something short to something very, very large. Okay, and we're going infinitely. I'm going to show you a little bit more about this. All right, I'm going to let you look at this website yourselves. You're going to find that I did put into the notes for today the website that we were going to look at, and it's for you to go ahead and look at in 3 dimensions at the structure of the graphite, and also in particular, I want you to be able to look at the structure of the diamond framework. Okay, so one of the things that I want you to be thinking about in association with today's lecture are the way that atoms pack in 3 dimensions when you make up a solid material. So you'll see why that's important in just a moment. And so we're going to have to go from bonds to bands in order to make this transition. All right, and that means we're going to have to talk about band structure today and where bands come from. This, by the way, the title for this panel, From Bonds to Bands, is actually the inverse of a title that was penned for a beautiful article written by Professor Roald Hoffman. And he was actually one of my teachers as an undergraduate at Cornell University, and he also won the Nobel Prize for his contributions to theory. And you know, I refer you to his article, From Bands to Bonds, if you want to learn more about this topic, because although the concepts of solid-state physics are often discussed with very different terminology than the concepts of electronic structure theory for molecules, there are a lot of very important parallelisms, and one of the things that Professor Hoffman is very good at is in bridging the gap between different branches of science that talk about the same things but don't realize that they're talking about the same things. And so here we have a system with a single orbital. So we're going to look at the number of orbitals. And here's a system with 1. And this is an energy level diagram. So we've used energy level diagrams for a lot of things. Last lecture we used them to discuss potential energy surfaces of chemical reactions in addition to all these other properties. Here's a system with one orbital. And then, as you know, when you have a system with two orbitals, you can get bonding and anti-bonding. This is the hydrogen problem. This might be a hydrogen atom, for example. Here's H2 molecular orbital diagram. And then we can consider a system that might have three orbitals. I'll populate it like this. And then if we have a system with four orbitals, it might be something like that. And 4 electrons. And so on. We see that one of the features is that the energy levels are starting to come closer together as we get more and more of them. Okay, there's 5. Here's 6. And then on to 7. And we start running out of room to draw them. That's 7. And so what people do then with this problem, we're only up to 7 and we've almost run out of space to draw these things. So what do? We draw them when we get out to infinity here as a band. So what the idea is that we have here, this band diagram, as we're going to call them, is a type of diagram in which we're representing filled orbitals down here as some kind of continuum. Because there's so many of them, an infinite number of orbitals that are all interacting in some extended solid material. We're going to be talking today a little bit about silicon and germanium and things like gallium nitride, in which you have a lattice that extends periodically in 3 dimensions. And so these molecular orbitals spread out and cover the whole material. So electrons can be anywhere at once within this entire extended solid by virtue of these delocalized orbitals. Okay? And then, just like in molecules, there are empty orbitals. And they occur also in a continuum. Okay? So I'd like you to get your mind around going from both ends to the same place in that type of continuum. And the idea that these band structure diagrams that people use to describe the electronic structure properties of extended materials are really molecular orbital diagrams. And so let's take a typical metal where n equals 3, principal quantum number 3. We start out, the atom has a 1s orbital. It has a 2s and a set of 2p orbitals. It has a 3s orbital, a set of 3p. Okay? And so there's an atom, like a sodium atom, for example. And here's our energy axis. And what happens is that each of these orbitals, that when you put all these atoms together into a piece of solid sodium metal, we've talked about that earlier in the semester, these orbitals overlap and spread out and form bands. And there's a band very low in energy that's derived from the 1s electrons in a metal like sodium, and it's completely full. And then there's a band from the 2s, and there's a band accordingly from the 2p. And then there will be a band from the 3s and a band from the 3p that I've run out of room to draw there. And notice that the bands that originate from atomic orbitals having the same principal quantum number here, 2s and 2p, are overlapping. In the case of a sodium atom, this 2s band is completely full with electrons. The 2p band is completely full. And this 3s band here, in the case of sodium, is half full. Okay, so furthermore, we're going to call these filled bands that are at the highest energy. This corresponds to our highest occupied molecular orbital. That will be called the valence band. And then up here, the lowest unoccupied band is called the conduction band. And so in the case of sodium metal, this 3s band is half full. And if we go over to magnesium, this same band is now full. 3s band is full. And if we go to aluminum, that 3s band is full, and the 3p band is partly full. And it's a consequence of the fact that the electrons in the valence band are right here at the same energy as the lowest part of the conduction band in a metal that gives metals their luster. It gives them their 100% optical reflectivity, these properties that we very much associate with metals. And so from analyzing band structure diagrams, even simplified ones, like the ones you'll find here and in your textbook today, you can really say a lot about the properties of different materials. Okay, so when you've got a meeting of the valence band and the conduction band, then your material is a conductor, and it's metallic. And then there are other possibilities, of course. You may have a valence band that is separated by some energy gap from the conduction band. And if that is the case, then you have a semiconductor, such as silicon. Okay, and then finally, you can have a large gap between your valence band and your conduction band. And in all cases, like with an MO diagram, we're putting these things on an energy axis. We're filling up electrons from the bottom in this material, energy from the standpoint of energy. And so you have a large gap here. And you have a material that is an insulator. And I think you'll appreciate why that is in a moment, but I want to bring Boltzmann's law to bear on the issue of electronic structure in extended networks like we're talking about today. You see, in materials like the ones I've drawn over here, the ability to conduct electricity is related to the probability of electrons being in the conduction band. So we need to know something about electrons in the conduction band. And using a Boltzmann distribution, we can write that probability as being related to 1 over e to the delta E over RT plus 1. And with an expression like this delta E here corresponds to our gap. And so it's possible then to go ahead and estimate the number of electrons that would be present in a cubic centimeter of your material in the conduction band as a function of this energy gap. And so we can consider that for materials like carbon or silicon or elemental germanium. In the case of carbon, I'm talking about diamond. And you should definitely go to that specified website and look at the diamond structure and try to get an appreciation for how the carbon atoms in diamond pack in 3 dimensions. From a hybridization standpoint, all the carbons in graphite are sp2, whereas in diamond, all the carbons are sp3 and tetrahedral. And completing this table, we can write down delta E in kilojoules per mole. The gap for diamond is 524 kilojoules per mole. For silicon, 117 kilojoules per mole. And for germanium, 66 kilojoules per mole. Okay? And that corresponds to here's the number of electrons per centimeter cubed in the material in the conduction band. And based on this large energy gap in the diamond structure, this value is on the order of 10 to the minus 27. Very small. This is an insulator. Diamond is an insulator. And on the other hand, silicon, number of electrons per cubic centimeter that are in the conduction band, on the order of 10 to the 9th. So this much smaller gap in the case of silicon, despite the fact that the silicon atoms also are tetrahedrally disposed with respect to their bonding, just as in the diamond case, we have a much smaller gap, 10 to the 9th, and that makes silicon, as you know, a semiconductor. And then germanium, 10 to the 13th. So even more, it's getting closer and closer to being metallic as the gap shrinks as we compare these materials. Okay. And having said that, we need to talk about the different types of materials that we can have. I want you to understand the difference between intrinsic and extrinsic semiconductors. If a semiconductor material is an intrinsic semiconductor, that means that it's a semiconductor in its pure state. Okay, and why would we make that reference? I mean, normally we're always talking about pure things, but actually you'll see in a moment that people do purposely make impure semiconductors for very good reasons, and we'll discuss that. Semiconductor when pure, and what that means is that you have a system like this with some kind of a small band gap, as we've suggested. Here's our energy axis, and what can happen is that either thermally or upon absorption of light energy, we can have promotion of an electron from the valence band into the conduction band. And so I'll draw that new situation over here. In other words, we may have thermal population of our conduction band, and we generate accordingly a hole. So in this intrinsic semiconductor, for every electron that jumps up into the conduction band and can then provide conductivity by electron transport, down here in the valence band, the missing electron generates a hole. And that hole can move around freely in the valence band. How does it do that? Well, it's a little bit like the mechanism that we studied earlier for translocation of protons in acidic water. You know, if an electron that's nearby the hole jumps into the hole, it creates another hole. The hole thereby moves. Okay? And so here we can have hole transport. In our valence band. Okay, so you can have conductivity occurring freely both in the valence band and in the conduction band for an intrinsic semiconductor of this type, where the number of holes is equal to the number of electrons. Okay, and you might begin to suspect that for an extrinsic semiconductor, the number of holes does not equal the number of electrons. Does not equal the number of electrons. Okay, so how does that work? In these extrinsic semiconductors, wherein you have differing numbers of holes and electrons, you're purposely adding a small percentage of impurities to your material. Okay, so let me draw two pictures to represent this. Here, I'd like to draw just a simple tetrahedron. So we're looking at a very small part of the silicon structure. Let me put the silicons in here in color. Okay. Each silicon is coordinated to 4 other silicons in elemental silicon. Okay. It's tetrahedral silicon all through this 3-dimensional material in which these bands have been created and in which we have valence and conduction bands. But what if we have synthesized our silicon with a little bit of boron impurity? Okay? If we do that, then boron goes into a position in the crystal lattice that is normally occupied by silicon. So boron finds itself surrounded by 4 silicons, each of which wishes to donate an electron to the boron to form an electron pair bond, but boron only has 3 of the needed 4 electrons to make those 4 2-electron bonds and to generate the octet, right? And so what happens is it wants to get an electron. And where can it get an electron from? It can get an electron from the valence band, from the HOMO of the system, okay? From what would be able to donate an electron in the system. So the way this then works is as follows. You should think about the structure of elemental silicon with a small number of boron atoms dispersed throughout that structure as creating localized negative charges that can't move because they're localized on these borons. Okay? And that generates for you a band structure diagram like this. You have bands, but then you have slipped in there a little orbital from the boron, a little electronic state here, intermediate between the valence band and the conduction band. So you have to choose your impurity correctly so that it has the right energy with respect to the valence band and the conduction band in order for the process that you want to occur. What this is, here's our boron derived state here, and it needs that extra electron because it's electron deficient when you put it in there. And so an electron jumps onto the boron, we'll represent that this way in the material, like that. And this electron is fixed in position. Because it is associated with a negative charge that has formed on the boron. And a corresponding hole is formed down in the conduction band. And this hole transport can give rise to conductivity. And so notice that in this type of semiconductor, and this, by the way, is a p-type semiconductor. P for positive. You're putting in a hole on that boron. So this is a p-type of semiconductor. This thing is stuck on the boron, and it generates a hole that is free to move in the valence band and giving rise to conductivity. So in this extrinsic type of semiconductor, you're not necessarily getting any conductivity up here in the normal conduction band, but down in the valence band due to the creation of the hole. And then the parallel situation to that, it would be where you have something that you dope into the structure that has one more electron than what's normally in the structure. So normally you're putting in silicon atoms, each of which has 4 valence electrons. So you put in a phosphorus atom, which is nearly the same size as silicon, but it's got 5 valence electrons. So you have this phosphorus in here, and it is tetrahedrally coordinated to 4 silicons, and there's only a few percentage of phosphorus atoms doped into this silicon semiconductor. And the phosphorus, what happens, it goes in there, it's got an extra electron, it wants to give it up so that it can have just an octet and form these 4 bonds to the 4 silicons. And when it gives up that electron, so electron goes out, that forms a positive charge that is localized and fixed on the phosphorus center in the structure. And so we can represent that as follows, where we have a phosphorus state that we had chosen appropriately in energy to go ahead and give up that electron. It gives up the electron to the lowest unoccupied orbitals in the system, which is the bottom part of your conduction band. So this electron jumps up off the phosphorus into the conduction band, and that leaves behind a hole. So you have a hole or a positive charge there fixed in position, and now you can have electron transport as your mechanism of conductivity up in the conduction band. So it's really, I think, quite fascinating to think about the way in which the concept of the octet rule and our understanding of bonding to tetrahedral centers can actually lead us to understand the mechanism of conductivity in solid materials that are either n-doped or p-doped here. It's quite clear. And then finally, I just want to take you through the way in which you can put these positive and negative doped materials together to create a device like a light-emitting diode. Okay, LED materials. These are obviously great things because you can generate light with a lot more efficiency in terms of energy than you can with incandescent bulbs. You can get them in all different colors. You know, these are finding application in so many different ways. One of the challenges that chemists have taken on is the discovery of light-emitting diode materials that are made of organic molecules, actually, conducting organic molecules that have properties correct for giving you very narrow emissions in the part of the spectrum that you want to have coming out of your light-emitting diode material. So chemistry is really very strongly involved in making next generation LED materials. But I just want to tell you a little bit about how these things work. The idea is that you've got these two types of semiconductors and you juxtapose them at an interface. So let me make the interface with blue. So you have a solid chunk of material here. This will be our N-type semiconductor, and over here they have a continuous, possibly two-dimensional interface here in this three-dimensional chunk of material, and you have a P-type doped part of the system over here. And in fact, normally this would be the same basic semiconductor material on both sides of the interface, and it would be just the doping that changes on the left versus the right. Okay? So this material might be something like gallium nitride. Now, notice that this is a 3-5 type of material, and this is gallium in group 13 and nitrogen in group 15 of the periodic table. So you add 3 and 5 together, and you get 8, just the same number of valence electrons you would if you had silicon and silicon. But these materials have the property that they are a direct band gap material. And as direct band gap materials, when the process that we're going to talk about here takes place at the interface, then out of this interface comes the light. Okay? And if your semiconductor material is an indirect band gap material like silicon is, then that is not the case. So the type of, and that has to do with the solid state physics of electronically, where is the conduction band located relative to that valence band? Is it shifted horizontally in solid physics speak relative to the valence band? That's what makes a semiconductor an indirect band gap material. If the conduction band is vertically situated above the valence band, then you get a direct band gap material. And so chemists, solid state chemists, are interested in designing new materials that have a direct band gap and that can release light when this process takes place at the interface. And on both sides, I just want to sketch the band structure for the materials. And I mean the gap actually to be the same on both sides here. And the difference is what we've doped it with. In the case of the negative material, we've got an electron up here in the conduction band that came in with, for example, our phosphorus atom and left behind a hole there that is fixed in space. And down here, we have our valence band all full. Over here, similar, except our material starts out with a hole down there because the electron has jumped up onto the dopant atom and become fixed in space as a negative charge, and that left behind a hole in the valence band down there like that. So what you've got is your N-doped material here on the left, your P-doped material on the right, and of course, what do you do then? You attach leads so that you can connect it to a potential difference. And when you do that, you want your anode to be over here so that the electrons can flow that way up to the N part of the device. And then electrons can flow this way, which means, of course, that holes go that way. And here's your cathode. And so you can think of putting on your potential difference in a system like this, and that has the effect of ripping electrons out over here. And if you rip an electron out, like let's say you take that negative charge back off of that boron atom, you pull an electron out to go ahead and reduce something down here in solution if you're using a battery for this sort of process, then, well, another electron can jump up here to take its place, but you're building up a potential here, And so what happens? The highest lying electron in the system over here in the N-type semiconductor is sitting there right at the junction, right next to where electrons are needed, so it jumps across. So electrons flow downhill here, and you can look at it like this. Electrons flow down there across the interface, and this is like as you put, when you hook this LED up to your potential difference supply, the electron flow is unidirectional. As the electrons jump across the interface, they're going from the conduction band of the N-type semiconductor. They're going down in here. Holes are being created. Maybe electrons are being pulled right off of that boron, and they're moving right across here in a process that leads to the emission of light right at the interface. So it's like a waterfall of electrons taking place all along this 2D interface. So electrons are just moving across this interface, dropping down in energy. As they drop down in energy, the energy, a photon that is the energy of this energy difference between the gap of this material, those photons are released for each electron that transits this barrier. And that's the principle of an LED. And I hope you're enjoying seeing this connection between molecular orbital theory for molecules being taken all the way to solid-state physics. So have a nice weekend, and we'll see you on Monday.